Cool. Welcome everybody to another session of the Portland Python Pirates. We have a guest speaker today. You won't get to hear my voice babbling on about whatever for the next hour, so enjoy that break. I have more in store, so don't get used to it. But the Portland Python Pirates, I have the website back up and running. Haven't updated some of the resources. I'd like to get some data resources and stuff in there. I have some of my own. If you have any favorite resources for anything you see there, feel free to send them our way and we'll be sure to add them to the growing list. And if you don't know what I mean, if you go to the webpage, you'll see a list of all kinds of Python resources that you can use. So yeah, and obviously Python related stuff. All right, so myself, Brian, and David are all kind of the organizers of the meetup, taking on higher positions, but essentially it's just fancy words for we're just organizers. They're not here this evening. They might be here a little later. If you see them pop in, feel free to say what's up. So community guidelines, we are inclusive, so people, all skill levels, all walks of life are welcome. Python focused, so we try to stay Python focused as much as possible, although we do have, from time to time, we do dip into other languages or something not so much Python focused, but primarily we stay related to Python. We do progressive learning, so we try to keep some kind of like beginner to expert timeline, right? So I would say this is probably an intermediate topic, right? Like if you have some familiarity with machine learning, this will probably be, it's just a deeper dive into a piece of machine learning, right? Like, or the machine learning lifecycle. So should be interesting. And collaborative. So, if you have something to add, if you have a question, anything like that, feel free. It's a very relaxed atmosphere. So jump into the messages or jump on mic. If you'd raise your hand, if you have something to say, that'd be helpful. So we don't interrupt right away if we're trying to like finish a thought or whatever, but definitely raise your hand. We'll get to you just as fast as we can. All right, so I'll start with announcements and resources. And as always, a funny meme that I pulled from the depths of the internet. And so we'll go over some announcements and resources. Murilo will do his presentation, and then we'll do a Q&A at the end if anybody has any questions or wants to discuss anything that was talked about during the presentation. So for announcements and resources, I'll drop these links into the chat. The first one is our next meetup. So creating and managing data science pipelines with MineaPy. So it's a open source project that I'm really excited about. It's related to, making a data scientist's life easier and a machine learning engineer's life easier, and kind of that collaboration, combining those two worlds, because a lot of people think that they're pretty related, and they are only in the machine learning aspect. But in terms of workflows, they can be very, very different. And so MineaPy is trying to help on the Jupyter Notebook side of things. So adding a lot of cool library, or adding this cool library there will help data scientists be able to kind of like package up their code and have it more ready for a machine learning engineer to kind of productionize that and get moving on building an entire MLOps pipeline, right? So capturing steps and so forth. So if you're interested in that kind of stuff, definitely check out their website. I don't have it on hand, but it's, look up MineaPy and it's pretty much the only thing you're going to see, right? They have an open source repo as well as a website where you can try Colab notebooks that will walk you through kind of the different aspects of what the library is trying to offer. I'll drop this link into the chat. This is just the link to our meetup page. So the next one, I already see some chatter in the chat about it. This is probably the best data science machine learning book ever written. Like, out of all of them, it starts very introductory. I read it when it was in its first edition. I have not read the next couple of editions, but they've added things like large language models, updated for the Keras API, which was brought on in TensorFlow 2.0. All the updates to Scikit-Learn. So they start off with, basic regression, data cleaning, that kind of stuff. And they move through different libraries, including Scikit-Learn, which you'll see tonight. Really great book, and always suggest it for folks. So here's a link to the O'Reilly page for it. I would say that that's my favorite learning resource. If you want to buy the book, obviously Amazon or somewhere else, or even directly from O'Reilly, you can buy it. I brought a podcast, data related. So Data Skeptic with Kyle Polich. Kyle's super cool guy. He started this way back in the day. I think he was very new to machine learning. So if you go back in the early episodes, he's like right at the beginning, just learning machine learning. Now he has guests on and they talk about more advanced topics and stuff like that. But still a really, really good podcast that I definitely suggest everyone should listen to. The most recent episode, I believe, is actually just very approachable for anybody who's even introductory to machine learning topics. Cool. So with that, I also wanted to mention that we're always looking for speakers. So if you have a cool topic, or even if it's just some project you're working on or whatever, like it doesn't have to be advanced. It doesn't even have to be machine learning, just as long as it's something related to Python or a developer workflow or something like that. We're interested in seeing it. There's people, we have almost, we have 1,100 members at this point, and everybody has different wants and needs, and they're all at different skill levels. So bring whatever you got to the table, and I'm sure someone will be interested. So if you'd like to apply to give a talk, and it's not really even an apply, it's really just fill out a form and we'll probably throw you in. But here's the form through the link into the chat. Feel free to click on that, the Google form, fill it out, and we'll get back to you and help you kind of get your presentation together. And that is all I have. I'll pass it off to Murilo and we'll get going. Murilo, take over.
Oh, awesome. Thank you so much, Chris. And yeah, thank you for just receiving me here tonight and allowing me to talk about hyperparameter tuning. Really cool stuff. So I'm actually going to stop sharing my video so I can focus on what I'm doing on my screen. But yeah, let's just start the presentation. So yeah, today I'm going to be talking about hyperparameter tuning. And this is basically what I want to cover for today. And it's not going to be like a part 1, part 2 series. I'm going to be talking about those things simultaneously. As I go through the topics, I'm also going to be going through the code. And I'm going to show you guys where everything is. So before I go any further, I just want to show you guys where all of the code is, if you guys want to check. Before I actually start everything. So if you go on my GitHub, you're gonna go into this page, and then it's gonna be this repo here called hypertuning. And if you click here, it's gonna have all of the information that you need to run everything.
Sorry to interrupt. I don't know about everybody else, but I don't know if we can see your presentation.
Oh, really? It says my screen is still visible to others. Let me do.
There we go.
Oh, okay, can you see it now?
Still can't see it. I just see like your image. Are you?
Can you see this?
No, you can't. Well, I can't. Can anybody else? I mean, maybe it's just me. Okay, no. Yeah, it's not just me.
Like you guys cannot see my slides at all? Okay.
Yeah, that's no problem. The static image. Yeah. That's so funny. So we like literally just tested it like 2 seconds ago. There we go. I can see your screen now.
Can you see now?
Yeah, we got kaleidoscope vision. There we go. Yeah, we can see the slides.
Okay, awesome. Yeah, so like I was saying, it's not going to be like a part one, part two kind of thing. I'm going to be talking about those things simultaneously. So you can go to my GitHub repo, and I also dropped the link in the chat. So if you go on that, on the repo, let me go here. You're probably going to be over here. And the repo is this one here called Hypertuning. So very on your face kind of thing. So you just click here, and all of the information they need is going to be here. Not a lot of information, but if you click here, it's going to be the Colab, where there's all of the code in a Google Colab if you don't want to download any dependencies or anything like that. But I'm basically going to be covering this notebook right here. I'm going to be covering that on VS Code, but it's basically the same thing as the Colab version. And I guess just a quick walk through Colab. If you click here, you can very easily just go to every single section that you want. But basically, those are all of the sections. And then you can just start running stuff like this. And then you just click run anyway. And you just keep running, and it's going to run everything. So yeah, it's the same one that I'm going to be going over on VS Code. So yeah, I can leave this right now and go back to the repo. And also the slides that I'm sharing here, you can just go here, and all of the slides are going to be on the repo as well. So, okay, cool. Going back to the slides. So this is what I'm going to be talking about. And by the end of the presentation, I really want you guys to understand what is hyperparameter tuning and why we're doing this, and also how we're doing this. And I'm actually gonna cover those as we go through. And also GridSearch and pipelines from Scikit-Learn, super useful to do hyperparameter tuning. So basically, before we go into hyperparameter tuning, we gotta understand what is machine learning. And this is just going to be a very brief overview, but basically machine learning is about computers that learn from experience. And when I say learn, I actually mean they're able to generalize, meaning they are able to understand information and they're able to make predictions. And experience comes with data. They look at data, and based on that, they are able to come up with a target function that maps inputs to outputs, and they learn this target function through function approximation, and every single algorithm learns a different function, and they have a different functionality and a bunch of different parameters, and that's where hyperparameter tuning comes in place, because every algorithm has different parameters, and then we use hyperparameter tuning to find the best parameters for those algorithms. So that's basically a very high level, and as you can see here, that's how a machine learning model kind of is in a very overview level. We have data, and then we feed that data into the model, and then we get predictions. And then it's really amazing. Every time I just run a model, I get myself just thinking about how amazing that is and how awesome it is to have a computer that are able to really learn and make those predictions and able to do really complex stuff. So yeah, so that's basically an overview. So going a little bit deeper into the pipeline and what it is, usually that data, we separate the data into training data and also testing data, but that comes a little bit after. So the data that we have, we usually separate into the features and the targets. And in academia, the features are usually related, or they're usually called as X, and the target variable is usually the Y. So we basically use those X's and Y's to find that target function, which is really a model. A model is just a mathematical function that finds the underlying relationship between those inputs and output pairs. In this case, we're doing supervised learning, so we're trying to find the function that best represents that underlying relationship between the X's and the Y's. And then we can make some predictions about that. And our data set that we're going to be going over and covering, it's going to be the breast cancer data set. And we can find the data set at the Scikit-Learn library. And I'm going to be covering that actually right now. So the X's are going to be all of the features in the data set, and the Y is going to be our target variable, which it really is the patient diagnosis. We're going to try to predict if a patient has some kind of malignant or benign tumor. And the X's are going to be all of the information from the patients. So if we actually go, and I have VS Code open right here, and this is really the same as the collab that you guys see, and I'll just make it a little bit bigger so you guys can see better. So basically, this notebook is going to be divided into 4 parts, and those parts get a little bit more complex as we go through. Especially this one, I kind of go crazy and kind of automate, or build an entire kind of auto ML grid search pipeline that is kind of really cool. And I'll show you guys as we go through, but just as you know, if you're new to Python, you're probably going to be able to really understand and pick up really good things about the early stages. And if you're more advanced, I also think there's going to be something for you, as we kind of use a lot of things from a lot of Python functionalities here. So let's just start by running those cells and importing those libraries. And here, like I said, Scikit-Learn has this breast cancer dataset that we just load from Scikit-Learn datasets. And we get the X's and the Y's. And the X's are all of the features, and the Y is the target variable. So if we run the cell, it's going to load the dataset, and it's going to get our X and our Y, and it's going to print the X and the Y shape. So here on the dataset, we see that we have 569 rows, and we have 30 features, and we have one target variable, which is the Y, that also has 569 examples. And if we do a Y counts, we can see their distribution. So we have ones and zeros, and the ones actually represent the benign patients, and the zeros represent the malignant. And we're going to be trying to predict which patients have a benign tumor and which ones have a malignant tumor. So that's basically the summary of the data set. And now let's actually train our first machine learning model. And we're going to be training a k-nearest neighbor. And I actually have it open. I think I have it open right here. I'm just going to, before we train the model, let's just go into Scikit-Learn. So this is Scikit-Learn's library. And for every single model, you can go and you can look it up, and you can see all of the parameters that are within the model, and you can see just really more information about the model. Because as we go through the hyperparameter tuning, we're really trying to tune those parameters that each model has. And for each model, they are different. They are very specific to the model. So if we go back, we're going to be creating a k-nearest neighbor, which is one of the most simplistic models that we can create. And basically, the Scikit-Learn API, the way how it works, you just import the model from Scikit-Learn. And then when you call it the model, we store that in an object. And when we call it .fit, it's going to fit our data, meaning that it's going to train on that data, and it's going to learn those underlying relationships between the X and the Y. And then we're going to be able to make predictions on that. And we're going to be able to score and see how well our model performed. So if we run this, it's going to do that. And then I'm just printing what model is, and then I'm printing the accuracy and the F1 score of the model, meaning that our model was, in this case, I'm just going to talk about the F1. It was basically 96% accurate, or it was able to correctly predict 96% of the patients. And here, if I do, it's not a decision tree classifier, it's just a, okay, there you go. If we just print that classifier, which is that object, we can actually look and just see that, yeah, it's an object from Scikit-Learn. And this is actually going to be useful in the future, because we're going to be able to see all of the parameters that belong to that object. And we can also do the same thing with a decision tree. So a decision tree, and I can go here and go Scikit-Learn. and then I can look at a decision tree. And as you can also see, the decision tree has a bunch of parameters that are very specific to what a decision tree does. And the way how we set those parameters is going to determine how well the classifier does on that data. And you can even scroll here, and there's a really, really good information. I really like Scikit-Learn's documentation. They do a really good job in explaining everything. So let's go back to that. And the same way that we did for the k-nearest neighbor, we can do for the decision tree, and it's gonna print, and we see that he had a 96% F1 score. Well, 95% F1 score. So they were pretty similar, both of them. And the cool thing about the decision tree as well is that from Scikit-Learn, we can call this tree dot plots, and it's something that is specific to decision trees. And we can see actually how the tree was built on that data. So in this case, let me just go back up here. The decision tree was built using this max depth parameter. And you may be thinking, what is that and what that means? So if we go back to the documentation, you can see that the maximum depth of the tree, it basically determines the nodes, how the nodes are expanded until the leaves are here. It basically just says how big the tree is going to be. And it's a pruning parameter that we use to control overfitting. And more of that a little bit later. So basically, when I said max depth equals 2, I'm just saying I want the tree to split twice. And that's going to be the maximum depth of the tree. It's not going to expand any further. And we can use those, the tree dot plot from Scikit-Learn, and we can plot that and just kind of see how the tree is being built. And we even have the features here from the data set. So this worst radius is one of the 30 features of the data set. So we can see, and the class is benign. So everything under 16.795 was classified as benign, and everything above that was as malignant. And then the tree kept splitting its data like that, because a decision tree is a greedy algorithm that recursively splits the data until you cannot split any further. And then it's able to make predictions or classifications on your data like that. So yeah, we just built a decision tree and then KNN classifier, and we got some metrics. So back to the presentation. This was basically what we just did. We had some data, we got our features, and we got our target, and then we built a model, and that model was able to really represent the underlying relationship between the inputs and the outputs, or the features in the target. And on that representation and the function that it learned, we were able to make predictions on that. So if we go further, this is a little bit how the pipeline works when we actually use the pipeline API from Scikit-Learn. Because right now, as I'm going to show you guys, usually there's some kinds of transformations and scaling that needs to be done on the data set before we actually train a data set. So what we did was actually wrong, and I did it on purpose so I can show you what's the correct way to actually do it. So basically, we're going to be using this pipeline API, and then basically all of this, now it's going to be the model, different from what we had here, that the model was just this little thing, and we're just feeding that data to the model. Now we're also going to be doing some kind of scaling to the data, really making sure that the data is representative and it's more robust to noise and bias. And then we're going to be able to make better predictions on that. And all of this right here, the scaling process and also the model that we built, is going to be the pipeline. And we also going to use the .fit and .predict, which is really nice because Scikit-Learn, even though we're going to be creating a pipeline, and it's not going to be either a KNN or a decision tree, it's actually going to be the pipeline API, we still can use the fit and predict, and we're still going to be trying to predict malignant or benign patients, tumors that patients may have. So let's just go back to the code, and we open up this. And then here, talk a little bit about scaling. So I just want to pause here and kind of explain the difference between scaling and normalization. Even though I don't have normalization here, I think a lot of people get that wrong. And normalization is basically the process of transforming all of your features in a range between 0 and 1. So all of them have the same range, per se. And scaling, it really, we're transforming the features so their mean has only one standard deviation. And it's a little bit different, both processes, but all of them or both of them are sometimes done, and they should be done before actually creating the model. And that's because, well, and I'm going to show you guys here why. So basically here, I'm just getting the columns, and I'm just putting the columns, basically just putting them as lower. And I'm also replacing any white spaces that they may have with the underscore. And right here, we can print, and we have this mean area and mean smoothness. And those are two features of our data. And if I print their max, or meaning the max value of each of them, we're going to see that the max value for the mean area, it's way, way higher than the max value for the mean smooth. And if I plot those, as you guys are going to be able to see much clearly, it's that they're not in the same scale. One here, its max value goes above 2,500, where the other one doesn't even go above 1. So for a model, when it looks at this data, it does not mean that this feature right here is 2,500 times more important than this one right here. They're just on different scales. And that's why we gotta scale our features before feeding to the model, so the model can understand better the importance of those features. And if we do that, we basically use the standard scaler from the Scikit-Learn pre-processing. So this scaling the features or doing any kind of scaling, it's a pre-processing step that we do before creating our model. So we instantiate the standard scaler object or API from Scikit-Learn, and we call it scaler. And we do the fit_transform, and we do that only on our features. We don't do that on our target variable. We don't do that on our Y. We only do that on our features. And if I run this, basically all of that transformation was done, and I saved that on axis scale, which is going to be separate from the axis, just so you guys can see. And if I run this, I get the same data. It looks the same. But if you guys look at the actual values, they were scaled down. So they are kind of in the same range between both of them. So now it's not like the model is going to prefer one feature over the other. It's going to basically have the same preference, or it's going to have the same weight under both features. And that's a good thing, because we really are interested in the relationship between them, and not really about that, this one, it's way more important than the other one. So now we gotta actually rethink what our model actually is. And for that, we're gonna be using the pipeline. So like I showed you guys in that presentation, we're gonna do both the scaling pre-processing step, and also we're gonna be calling the model, and we fit that, or we put that inside the pipeline objects from Scikit-Learn. And also, if you go here, let me show you guys. If you go to Scikit-Learn, there's also a pipeline documentation, and it basically explains to you what is a pipeline and how you can use one. And it has a lot of good stuff. So I highly recommend going through Scikit-Learn documentation so you can better understand that. So basically on the pipeline, we do that. We are going to be scaling your features, and then we're going to be instantiating your model. So, and the good thing is that the pipeline calls .fits, and then we can call it .predict and .score the same way. And I'm going to go up here. We can do that the same way that we did for the decision tree. Is basically the same API that we do, we just call it on the pipeline instead of calling on the actual classifier. So if I go down and we run this, it's gonna build, and look at that. The KNN did 98.5% F1 score. So we basically improved 3% from our KNN classifier that we built before by simply doing standardization on our features and nothing else. No hyperparameter tuning. Just by standardizing our features, we're able to improve our model by 3%. And if we call .pipe, remember that when we call it the classifier itself, he only returned the classifier, but now that we call the pipeline, we call this pipeline objects, and then it basically says what it is. So it has 2 steps. It has the scale step, which is a standard scalar, and also the model that is the KNN classifier, basically those right here. And the standard scalar is just a standard scalar, and the KNN is just a KNN. And it doesn't have anything inside because, again, we didn't fit, or we didn't even show any parameters to the model. So it's just the model itself to the default parameters, which is probably another thing that I should talk about, actually. So if I go back and I just go to the KNN, you're going to see that each parameter, just because we didn't call it, doesn't mean that it doesn't exist. It's actually, when you call the KNN classifier, the K-neighbors classifier, it basically comes with the parameters with some default values. So if you call KNN without anything inside, if you don't pass any parameters, it's going to have all of those default parameters right here for each one of them. So yeah, and then we can actually call the pipe.scale to just get the extended scalar, and we call pipe.model to get the K-neighbors classifier. And we can do the same thing for the decision tree. So if I run here, we're going to see there our decision tree. It actually didn't do really well. It kind of did the same as before. And that's really just because how decision trees work. Decision trees, they don't actually need any kind of scaling because how they are built. Remember when I said that there are greedy algorithms that recursively split the data until they cannot split the data any further and then be able to make predictions? Well, in the splitting process, they just look at the features with the most information gain, and that's how they define how they split the data. So the features don't really need to be scaled. And also you can pass data, or you can fit decision tree classifiers with data that has, well, for data sets that have missing data. So they're also robust to missing data, and they are also a little bit robust to outliers. And really, really nice to interpret, as you guys saw in the plots that we did. We could do the same here and just see how the decision tree was built. But yeah, they're really nice to be interpreted. And we can even run different pipelines. And by that, I mean, I'm just basically making a function here where I'm passing the pipeline, and I'm passing the X, and I'm passing the Y. And then it's basically doing all of that for us. So we don't have to repeat our code. So if I run the function, and then I create a KNN pipeline, and I create a decision tree pipeline, and I call the fit predict function that we did it up here, it's basically going to do all of that for us. And it's going to print our metrics. And that's really cool. However, we're making a huge mistake. I mean, if the gods of machine learning were looking at us right now, they would be rolling their eyes and saying that we are not worthy because we're using our entire data to train the model and make predictions. And that's really, really bad, because now we don't know how the model is actually able to generalize to new data. And this is just really, really bad, because machine learning is all about generalization. We just care about how the model does on data that has not seen yet. And to do that, we gotta split our data, and we gotta split our data into a training set and a testing set. And we use the training sets to feed the data, to feed the model and to make predictions. And then we hold the testing sets. We do not show to the model, and we just use the testing sets to just, like it says, to test how well the model that was trained performs on data that has not seen before. And this is what I mean by generalization. And I guess if I could just make an analogy.
Hey, Murilo, can you hear me? We can't hear you if you can hear me. Okay. Give me 1 sec, guys. Yeah, me too. I thought it was me, Tony. I was like, oh God. I thought my wife was running the microwave. That was every time she runs the microwave, our Wi-Fi just kills my connection. Or I mean the microwave kills my connection. Hold on. I'm gonna message him on just outside and just let him know. Oh man. Oh, there he goes. Okay. There we go. Yeah. He knows. Go to your settings, Murilo. Should be able to see it, like your settings, the triple dot down there at the bottom. Or can you hear me? I don't know if he can hear us either. Yeah, no, we can't hear you. Hold on, everybody. Sorry. There's nothing I can do on my end. Yeah, that's a good idea, Sean. Okay, cool. He's leaving and coming back in. Just give it 1 sec, guys. Sorry. See if that worked. He joined.
Can you hear me?
Yeah, we got you.
Okay.
Cool. We only lost you for like maybe 20 seconds. I think you were just describing the training test set and stuff.
Okay. Okay, cool. Maybe right now would be a good time to actually pause and ask you guys if you have any questions that I can talk about. So let me put the presentation back up. I think it's this one.
Cool.
Okay, can you see my screen?
Yes.
Okay, awesome. So yeah, I think I was talking about generalization and train test play, right?
Correct, yes.
Okay, awesome. Before I move any further, do you guys have any questions? Because I've been talking for like 40 minutes. I should have thought. I mean, we have a very small group. Do you guys, are you guys like familiar already with machine learning and stuff? I'm assuming yes.
I know it's varied. I mean, people can answer for themselves, but I know it varies in this room right now because I know some people. So from very familiar to not familiar at all. So I think what you're doing, you're on the right track. You're doing great.
Okay, cool, awesome. I would just keep going then.
Yeah.
So yeah, so going back from the idea of actually doing a training and testing and splitting your data, the way how we were doing before, just using the entire data to train and then the entire data to test, is just bad because the model is not really learning. It's just memorizing those X and Y pairs, and then it's able to make predictions on that. But in the industry or in life, I guess, we actually care about how the model is able to make predictions on data that has not seen before. And that's why we do train test split. So this is how we do train test split using Scikit-Learn. So from Scikit-Learn model selection, we just import train test split. And then we're going to have our X trains and our X tests and Y train, Y test. And some things to notice, you may be asking how much data goes into training and how much data goes into testing. And that varies, and you can definitely play with that. Also, really depends on the size of your data and kind of what kind of data you have. But for this example, since the data only has 500 rows, I'm just doing a 80-20 split, which is really common to do. It's something that's super common in the industry and also academia. So basically 80% of the data is going to the train set and 20% is going to the test set. And this is stratified thing right here. I'm going to talk more about that later, but basically it's a technique that preserves the distribution of our data. So the test set is representative of the distribution, saying that, if we have some classes like we had before, the data was kind of imbalanced, which I'm also going to be talking about. We want to make sure that the same distribution of ones and zeros for the classes that we want to predict, they are representative for both the training and the test. And this random states equals 42 is just something that you're going to see throughout the entire notebook. And it's something to basically just enforce reproducibility, or just making sure that every time we run this, we get the same distribution and the same results. Basically, just making sure that everything that we do here is going to be consistent at every run. Because as you guys can tell, the process of splitting the data requires some randomness, and the random states just making sure that it's basically just a seed. So if we run this, we get that we have a train data and a test data, and then out of the 569, I think, instances, 455 go to the train set and 114 goes to the test set. And this 30 is just the number of features that we have. So it's basically data sets of 455 rows by 30 columns. And then we have one column of 455 rows for the Y, and the same kind of works for the test set, is the same representation. And another thing that I want to point out is that our data is highly imbalanced. And by imbalanced, I mean we have 357 instances or examples, or 357 rows that were, or patients that were diagnosed as benign, having a tumor that was classified as benign. and 212 of those as malignant. So we gotta actually, models don't like this. They don't like data that is imbalanced, because then let's just assume that we have a data set with 100 rows, only 100. And we have 90 of those rows belonging to one class and 10 of those rows belonging to another class. We could just easily say that if we're very, very lazy, we can just classify as all of those 100 rows belonging to the 90 class. If we do that, we're going to be 90% correct, because we just classified everything as being one class instead of the other. And that's okay for that class, but for the other one, we would be 100% incorrect or 0% correct, because we were not able to classify any of those examples as being the other class. So in one way, we were very effective in classifying all of the 90 examples, and the other one, we were very ineffective of classifying the other 10. And that's why we want to have kind of the same distribution of the classes, so our model can, learn those relationships in a more fair way. And if we do this, basically so here's not Scikit-Learn, as you might have noticed. It's called IMB-Learn, and IMB it stands for imbalance learn. And SMOTE is called a synthetic minority oversampling technique. And it's basically just an oversampling technique that is going to say, hey, out of those, 357 and 212 instances, how I can balance that, meaning I need more instances or more malignant examples in the data sets up to 357, so they can have the same number. And if we do that, we just call SMOTE, and we save that on an object, and we call fit underscore resample, and we do that on the X train and XY, the X train and the Y train. And we do that, why we're passing the Y train, that's because we actually want to, the 212 classes, they are in the Y. So we need that representation to see how we're gonna reshape the data set, how we're gonna do this oversampling technique. And if we run this, we get, now before we had 455 rows on the training data, and now we have 570. And if you actually do some math, that's actually the difference between, it's going to basically be the difference between 212 and 357, where we're also doing the splitting on 80% on one and 20% on the other. So it's accounting for that as well. And you might have noticed, we do not do oversampling on the test data. We leave the test data the way that it is, because the test data is our source of truth and represents the data that we would actually see on the real world. So we don't do any oversampling on the test data. We just do for the training data, so the model can better learn those relationships between those two classes. And if we do the value.count, we're going to see that for the training data, we have the same amount of classes for both benign and malignant. And for the testing data, it's still imbalanced. But that's good, because that represents reality. And that's what we want. And we can kind of put all of those steps together, at least for the pre-processing parts, into one little function. And here we have the load breast cancer basically objects or API from Scikit-Learn. And we're just going to be calling our X's and Y's, getting that data. And then we do the train test splits. On the function itself, we're passing an attribute called oversample. And if we set that to true, it's going to do the oversampling. And if we don't set to anything, it's not going to do any oversampling. And then it's going to return the X train, X test, Y train, Y test. And if we run this, we get that. We just run the function. And then if we actually run that, we're going to get the same data that we got here. But it's quite nice, because then you can just run the functions to get the data. And then we can do, we can train our pipelines, we can train our learners, put them in the pipelines, just like we did last time. And then we can call the fits predicts, which is that function that we did. And they did kind of okay. Decision trees are not doing as well as k-near neighbors, but I think we can actually help that, and we can actually find those parameters that best fits the data, doing some hyperparameter tuning, which is going to be the next parts. So let's go back to the presentation. So before I jump any further and I show the next slides, do you guys have any questions about this? Can you guys still hear me?
Yeah, we can still hear you.
Okay, cool. I have not been talking for like 5 minutes on my own then. That's good.
No, you're good. Your microphone still works.
Okay, that's awesome. Cool. Anybody has any questions, or can I move on? Okay, silence is accepted. So I'm just gonna move forward. Okay, so this now it's gonna be our new pipeline. And as you may have noticed, we changed quite a few things. So we added this little weird thing right at the bottom. I don't know what it is, but I'll explain to you guys. And there's also this max depth thing. I don't know what it is. The pipeline still kind of looks the same. And then we still have our predictions. But there's a thing called GridSearch here at the bottom, and we're calling a model. So how does this actually fit everything? So before we actually were thinking that the scaling process and then the classifier that we were calling or we were instantiating, we were putting that inside a pipeline, and we were calling that our model. But now I'm going to introduce something called cross-validation that basically just increases robustness on the training process and makes sure that the model actually sees the entire data during the training phase and is also get validated. And that basically just introduces statistical robustness to the model. And it's a really good practice to have when building any kind of machine learning model. And also, like I said before, every single learner that we build, it's going to have its own parameters. And those parameters are going to be specific to that learner. And then maybe changing those parameters is going to help, or oftentimes is also not going to help the performance of that learner. It can either improve or it can make it worse. So we kind of want to find the set of parameters that perform the best and can make the best predictions and basically just have the best model. And this max depth right here, it's a parameter that belongs to the decision tree. We actually already used it, and we set it to 1, or we set it to 2 actually. But you can really set to kind of any number, and that basically just controls how deep the tree is going to be built. And the decision tree itself has a lot of parameters that you can play, and all of them are in the Scikit-Learn documentation. So if I just go, so basically just as a recap, before the pipeline was our model. So now this GridSearch API is going to actually be our model. And I'm going to actually be talking more about what GridSearch is and what it does. But that I'm going to be talking in the code itself. So let me open up part 3 GridSearch. So basically, right here, basically explains what GridSearch is. It's basically just a technique to find the optimal parameters for a machine learning model. And then the hyperparameters are those values or the weights that we change, and they determine how well the model is going to be. And hyperparameter tuning is basically the process of finding the best values for those parameters. And that depends on the given machine learning model and also the task that we are trying to do or the problem we're trying to do. And by that, I just mean it really depends on the data set. So the parameters of those models, the values of those parameters of those hyperparameters is going to vary depending on the data sets that we have. It's going to vary depending on the task that we have. So we're training those learners here on the breast cancer data set. If we're training the same k-nearest neighbors and the same decision tree on a different data set, they would have different parameters. At least the optimal parameters would be different. And also coming back to that stratified sampling thing that I was talking about, we're going to be using stratified sampling during cross-validation. And that's going to basically ensure that the population is divided into homogeneous groups. And that basically guarantees that the test set is representative of the overall population. So it's just a really good thing to do when performing cross-validation. And perhaps I didn't really explain what cross-validation is. So let me just go back here and kind of just talk about that. So basically, cross-validation, we're going to be training the model. Before we're training the model, we divide it into the train sets and the test sets. But when we were training the model, we trained on the entire data. And that's also bad because we're not seeing or we're not evaluating how well that's going to be. So now on that training data, we're going to separate the data basically into those things called folds. And we're going to use those folds. We're going to use some of them to train the data and the other one to predict the data. And we're going to do that multiple times. In our case, we're actually going to do 5 times, but here we're doing 3 just as an illustration. And each time we are changing the training data with the prediction data. And we're doing that so that the learner can see the entire data set during the training phase, and basically just introduces a lot of statistical robustness to the learner as he can train on the entire training data and also make predictions on that. So it's basically going to train once on this data and make some predictions, and then it's going to train another time, but then it's going to train on different data and make a prediction, and then it's going to train a final 3rd time on a different set of the data and make predictions on another set of that data. And that really ensures that the learner trains and uses the entire data to train and to make predictions. And all of that is just using the training data. The task data we do not use for any kind of cross-validation. So yeah, so that's basically what it is. And here on the document, I put some links for the GridSearch, also decision trees and k-nearest neighbors. I think I also have those links at the top of the document, but I thought that here right now would be a good time for you guys to check it out. Like if you're doing this on your own at home later, this would be a good time to actually go and see what they are, and also check those parameters, because we're going to be playing with them right now during hyperparameter tuning. So like I said, each learner has different parameters. And here we have our decision tree learner that we fetch into the pipeline. And remember that it was under the model thing. So if we go up here, I'll show you guys what I mean. So pipe model, here's a k-nearest neighbor, but the decision tree is the same. And basically, here's the pipeline, it has a standard scalar and also the model itself. And if we go back, right here, when we create a model, we're basically doing a scalar and a model. And when we call the pipeline model, we're basically getting the model objects or the classifier objects from Scikit-Learn. And then if we call get params, it's going to get all of the parameters that belong to the decision tree classifier. So all of those here, the alpha, weight, criterion, max depth, max features, all of those right here, they're all hyperparameters. And all of those can be tuned and they can be tweaked to make the model, basically to make the model make better predictions. And all of them can be optimized. And hyperparameter tuning is basically the process of finding the optimal values for those parameters. And we're going to do that using Scikit-Learn's GridSearch. So from Scikit-Learn model selection, we're going to import GridSearch and also the stratified k-fold cross-validation, because that's how we're going to be doing cross-validation inside GridSearch. And basically, here is the same as before. We just initiate a pipeline with a scaler and the learner itself. And here we're gonna, this is the different part. Here's where we're gonna fit the parameters to the learner. So those here model, why did I say model? Because the learner is called model. And this, the scale in the model can be anything. Like if I said ABC, whatever, it could be whatever. It doesn't have to be model, it could be whatever name that you wanna have. Some people call CLF for classifier. I just call it model. So, you know, it's easy to understand what it actually is. And the parameters is going to be a dictionary. And you always instantiate with the model and then double underscore and the parameter name itself. So criterion was actually one of the parameters, and you can see here. And then max depth was another hyperparameter, and minimum samples per leaf was another hyperparameter, which is right here. And each one of those, the way how you change them, it varies, is gonna greatly affect how the model learn. And you know, this is why I put the documentation here at the top, because right now would be a really good, really good time to just take a step back and look at those classifiers and see what those hyperparameters actually mean, or how changing them, like what is Gini, what is entropy, and what that means. Basically, I can kind of explain. When I said that the decision tree classifier, the model itself, the algorithm, recursively splits the data, and it splits by getting getting the feature of the data sets that provides the most information gain. The Gini and the entropy are just functions that calculate how much information gain each feature is going to provide. So they are different functions, so therefore they're going to calculate different ways to get those the information gain depending on the feature. And we're gonna try to find which one of those is gonna be the most effective into creating our decision tree classifier. And we do the same thing for the max depth and the minimum samples of leaf. Those are just lists that they range from 1 to 10. I mean, here says 11, but it's not exclusive. So basically, we're just passing lists. And this is another thing. We gotta pass lists to those hyperparameters whenever calling, whenever instantiating that dictionary. And we do that. So the stratified k-folds are just going to be a cross-validation. We're going to do 5 folds. We're going to be shuffling the data before training and random states to just make sure that is consistent between runs. And we're going to initialize our GridSearch objects. And we got to pass something. So one thing that we got to pass the actual pipeline, the scaler and the model itself. The other thing we're going to pass to GridSearch is going to be the hyperparameters and what their values are. We're also going to be scoring the model on an F1 score, but it could be accuracy, it could be recall, it could be any kind of scoring method that Scikit-Learn provides. You can even compute your own scorer, and you can make your own function to score your data. But F1 is the one that I'm going with. Also, the reason why I chose F1, it's because our data is in balance, and F1 provides a good balance between precision and recall. Basically, it's a summary of those metrics. And whenever you have imbalanced data, it's a good basically rule of thumb to use the F1 score or something like the ROC and AUC curve to get the performance of your model. And we're going to be doing, like I said, we're going to be doing cross-validation on 5 folds. And this verbose equals 2 is just going to say, it's just going to print stuff. It's going to print how our model is kind of learning. or basically how many instances we're building from the GridSearch API. And the end jobs is just going to say how much computing we want to give to GridSearch. And -1 basically says, I want all the computing. I want this to run as fast as you can. And if we run this, we basically just instantiate everything, but we don't train it. And the good thing about it, GridSearch, is that just like pipelines and just like our model itself, we can call the .fit, and then later we can call it also .predict on GridSearch. And we are going to be feeding our data on the training data, and then we're going to be saving on this DT CLF objects. And if we run this, it's going to say, oh, hey, we're feeding 5 folds here from cross-validation on 200 candidates totaling 1,000 fits. And I'm going to explain why 200 candidates and why 1,000 fits. So as you can notice, it's still training. And because basically what we're doing, we're building 1,000 models. And that took 22 seconds to run. And basically what GridSearch is doing is that for each one of those hyperparameters, it's setting those, and it's basically just looking at all of the combinations possible within that hyperparameter space. And I'm going to be talking about hyperparameter space, and I'm going to actually go through what that is right now. So basically, criterion has the criterion hyperparameter has 2 values, Gini and entropy. Max depth has 10 values going from 1 to 10. And then the minimum samples per leaf has also 10 values going from 1 to 10. And we're doing that, we're doing a 5-fold cross-validation. So every single cross-validation or every single iteration, we're building the model 5 times. So basically, if we multiply all of that together, it's going to give us, and we run this, is going to give us, hey, we're building 200 models, 200 because 2 times 10 times 10, that's 200, 2 times 10, 20 times 10, 200. And then we're feeding those models 5 times at each iteration. So 200 times 5 is 1,000. So that's basically what we're doing. We're feeding 5 folds for each of the 200 candidates, 200 different combinations of hyperparameters. And that's going to total into 1,000 models that we built. So you guys can imagine that, I mean, if we go up here and if we try to do, like different combinations for every single hyperparameter, it's going to be a lot. It's going to be a lot of computation. And then you guys can also imagine that that gets super, super hard if we're talking about something like deep neural networks, that they already require a lot of time to train. And they also have a lot of hyperparameters, way more than a decision tree does. And so, yeah, it's quite a lot. And if we call the DT classifier, you're now gonna see that it's a GridSearch objects. And then within the GridSearch objects, if we expand, it's gonna have a lot of things. It's gonna have the cross-validation that we did. We did a 5-fold cross-validation, and we did shuffle and random states. And then within the GridSearch, we're also going to have our pipeline. That's going to be our scalar and our decision tree. And then we can check those as well, decision tree and the scalar. And then we can also even check our param grid, which is what I was calling. And basically what the param grid is basically all of the hyperparameters and their values. So here we have that list that I said goes from ranging from 1 to 10. And the minimum samples per leaf also ranging from 1 to 10, and Gini and entropy. And basically all of the information that we built to create the model is going to be stored on this GridSearchCV objects. And we can even call it the best estimator. And the best estimator, and this is really cool, is going to be out of those 200 candidates that we built, which one was the best based on the F1 score, because we provided the F1 score. So that's going to be the scoring criterion. So based on the F1 score, which of those combinations was the one that performed the best? Meaning, what are the combination all of those parameters that created the best model. So it's going to be the one that max depth is going to be 7, and the minimum numbers of leaves is going to be 3. And then we also had another one. So if you actually call it best estimator, and then you can get all of them. And just like this, if we call the best params, it's going to get the best parameters that fits that model. So it's going to be the Gini providing the most information gain versus the entropy. So Gini was better. The maximum depth is going to be 7, which is, we can see right here. And the minimum samples per leaf is going to be 3. And that was it. And so that combination of Gini 7 and 3 was the values of those hyperparameters that provided our best model. And then we can kind of make predictions on that. So the train score, the test score, we just call that objects, the GridSearch objects, and we just do dot score just the same way that we're doing before. And then we're able to see that it performed really, really well on the training data and not as good on the test data, but it's still a really good model. It was able to correctly predict 95% of the benign malignant patients based on their tumor. And if we do the F1 score, it's going to be the same because, like I said before, we use the F1 score to train the model. So when we call the classification, the score on the test data is going to have the same score because that's what we use. So then you don't have to do only F1. You can do any performance metric that you want. And here I have a lot. So I'm just going to run this and show you guys. This is basically how the model decision tree classifier, we use a GridSearch, and I'm just printing all of that stuff here. And this is how you perform on a variety of metrics. You don't have to do F1. If you want, you can do any kind of metric that you want, just making sure that the metric that you choose makes sense for the data set that you have. So for me, I'm doing a imbalanced data set, and I want to make sure that my learner has a high F1 score. And so that's the score that I chose to train the learner, and the learner was able to optimize to that score. And that's kind of what we see here. And then the other really cool thing about the GridSearch is that we can get all of the results into a pandas data frame. And if we run this, it's going to get us a data frame that's going to have 200 rows, and it's going to have a lot of columns. So it's going to show you a bunch of really good stuff, like how long it took to fit. And that combination that I was telling you guys about, like the Gini, the criterion, the max depth, and the minimal samples per leaf. So on the first iteration of cross-validation, the model had the Gini as the criterion hyperparameter, 1 max depth, and 1 minimal samples per leaf. And then on the next iteration, it had Gini 1 and 2, Gini 1 and 3, Gini 1 and 4, and it goes that until it's going to be Gini 1 and 10. And then after we go through all of those combinations, it starts again for Gini 2 and 1, Gini 2 and 2, Gini 2 and 3, and so on. And it has a really good stuff. And here this rank test score basically ranks out of those 200 models that we built, which was the best model. And it goes from 200 all the way until 1 being the best model. And here we have a bunch of the same numbers because those combinations had the same score on our model. So those models right here, they kind of scored the same. They had the same score, basically, the same F1 score. And we can do the same thing for the K nearest neighbor. So if we run this, we start the pipeline, and we also get the KNN GridSearch. Just notice that the KNN is going to have different hyperparameters than decision tree, and that's basically how KNN works. So like I said, each model is going to have a different set of hyperparameters, and that's going to be exclusive to the learner itself. So we do that, and then we do fit. And it's going to say 5 folds for 40 candidates, totally 200 fits. So we don't have as a big of a grid search space as we had for the decision tree. But yeah, so it's training, and it's gonna take like 20 seconds or so. And then now it's done, and we can actually check the best estimator. It's gonna be that the metric is gonna be Euclidean. It's gonna have 20 neighbors, and the weights is gonna be the distance value for the weights. And this is really good. You can go check the documentation and see what those parameters mean. And that's basically it. So we can do the same thing that we did. We can get those metrics for the KNN the same way that we did for the decision tree. So if we run this, we're going to get GridSearch KNN, and then we have those metrics. And if we see the test score and the F1 is going to be the same, and it scored really, really, really high on the train data and not as high on the test data, but that's okay. And that's basically how you run GridSearch. And then now, I'm also going to stop before going to part 4, but now it's going to get very fun because we're going to do a lot of crazy stuff, and we're going to search through a huge hyperparameter space going and just looking at more models. But before I talk any further, do you guys have any questions? I know I'm probably already over time. So let me know if you, like Chris, let me know if you want me to stop, or I don't know.
I think we had you set till 6:30 Pacific, right? So it's up to you how much longer you want to go.
Okay, no, I can go. So let me just go kind of quickly on part 4. I mean, you guys have this notebook, so feel free to just play with it. So basically, what I try to do on this part 4, it's basically try to, if I was actually doing this at either my job or just doing from a machine learning perspective, this is something that I kind of said, that machine learning is first and foremost a software endeavor and requires experience building well architects and reliable and easy to deploy software. And as you guys can see here on the top, we are repeating ourselves a lot. Every time we create a learner, we're basically just reusing all of the codes, and we're basically just doing a lot of copy and pasting. The only thing that changes really is the pipeline that belongs to the learner is going to have a different learner, and also the param grid for that learner. So that's going to be specific to the learner itself. Everything else, the grid search and the cross validation, everything's going to be the same. So how can we build kind of a pipeline that puts everything together in a nice way? And the way how I did it was by using classes. And also, we're only using 2 learners. What if I want to build more algorithms? So here I'm going to build not only a KNN and decision tree, I'm also going to build a XGBoost classifier and also a neural network, which is called a multi-layer perceptron from Scikit-Learn. And we're also going to use bigger parameter spaces for those. And we're going to use something called a randomized search, which has the same principle as a grid search, but instead of checking every single combination possible, it's going to check random combinations. And a randomized search is really popular on academia for really running different models and checking their performance against themselves. So I'm just going to run this. And what I do is I create this learner class. And this is a lot of code. For the sake of time, I'm not going to go too much in depth into that. But you guys can check this. So basically, I have some functions. And this one, I'm just feeding the grid search. I'm saving a lot of the metrics into that. And here I'm getting the score of the learner. And then this one, I'm evaluating and printing the score. And that's basically it. So if I run this, did I run the cell book? I did, okay. So now we're gonna have our pipeline setup. And basically I just have a function called learner setup. And here I'm gonna have my KNN setup. I'm gonna have my decision tree pipeline. I'm going to have my XGBoost pipeline, and I'm going to have my multi-layer perceptron, basically my neural network pipeline. And as you can see, I'm passing a lot of hyperparameters to the XGBoost and to the neural net. And that's just because they are more complex algorithms, and you can tweak them a lot. You can really make them perform really, really well, and they're going to perform much better than the other ones, as you guys are going to see. And I call the learner class, and basically I just initiate that class with the pipeline and the param grid for each of those learners. I put those into a list, and I return that list. So if I run this, I'm going to basically run a randomized grid search on that list. Basically, for each learner on that list, I want to train the learner on a grid search. And I also want to get the scores for that learner. And if I run this, it's going to run. And I'm just going to like run the other stuff too, because I just checked the time. But this is going to take like not too much time, because now the randomized search, instead of checking every single combination, is checking random combinations at most 50 times. So I put that var, it's kind of nice. So yeah, so now all of our 4 learners are already trained. If I open this up, I basically print a lot of stuff just to check how the training went, so I can compare. So the k-nearest neighbor had a perfect score in the training set, and F1 was 95.8. I think it was an improvement. And the decision tree classifier as well improved a little bit. The XGBoost performed really, really well on the test sets, as you can see. And then the neural network also performed really, really well. And then on each one of those, I'm also printing the best parameters for them. I'm printing a classification report. I'm printing all of those metrics. I'm also printing how long it took to fit the learner, and how long it took to make a prediction for each of those learners. And if I basically run this, I get back those learners into their respective objects, and I can learn those 4 really quickly. Each of them have their own respective pipelines and the best estimator, so I can like open up and I can see like XGBoost has a lot of stuff, and the classifier also. And then I can kind of compare their performance. So to do that, I'm going to create some learners without actually tuning them, just the basic learners. And I get some scores for each one of them. And then here I'm going to train the tune learners using GridSearch, and they're going to have static parameters. I'm not going to change them. They're just going to be the best parameters that we had from the randomized search. And I'm just going to run that and train. It's going to train rather quickly, because those are fixed, so the hyperparameter space is quite small. And here, I'm basically just getting the results. So I'm printing the results, and then at the end, I'm kind of just running, and I'm getting their metrics, and we can kind of compare how each learner performs without being tuned, and how they performed after GridSearch. As you can see, all of them improved after we kind of set the parameters for optimized values. And that's basically it. Like, that's basically what the presentation is. So kind of tying everything together, the what, why, and how. What is a hyperparameter tuning is basically just that process of finding the best hyperparameters for a given machine learning model. And the hyperparameters are those values or weights that determine how the process goes. And why we're doing this is basically, the performance of ML models is highly dependent of those values. So choosing the right hyperparameters to tune is really critical for achieving good model performance. And how we do that? We do that by using pipelines together with GridSearch. Another thing that I want to point out is that the XGBoost model that we built right here, basically XGBoost is not from Scikit-Learn. XGBoost is on its own thing. It's not a model from Scikit-Learn. But one of the really nice things about both GridSearch and also randomized search is that it allows you to fit other models that don't belong to Scikit-Learn and you can still do hyperparameter tuning on them. And that's really cool. And also, just to, I guess, finalize the presentation, some things I do not cover just for the sake of time, or it was kind of beyond the scope, was that the data set did not have any missing data, but you can kind of add a simple imputer to that pre-processing pipeline. Really, like with standard scalar, you can kind of put another pre-process step there, a simple imputer, for if you have a data set that has missing data. And also, we didn't have to do any column transformations. And we didn't even cover learning and validation curves, because you can use those to see and to check how the learning process is going. And some supplemental material, I'm really glad that Chris mentioned Hands-on ML, because that's a really good book. And you can kind of get a lot of that stuff, the stuff that I covered in that book. And that's basically it. So yeah, here's where you can find me. You can find me on LinkedIn and also on GitHub. And yeah, that's kind of it.
Well, god dang, man, that was a good presentation.
Thank you.
Yeah, there's a lot of detail there, tons to take in, and it's cool that you guys have those notebooks. I highly suggest you go back through those notebooks and really understand what's going on, you know, explore some of the different, like you said, the hyperparameters, any parameters. By the way, are there any questions? I have a couple comments to make, but are there any questions before I make those comments from anybody? People have funny things to say.
Yeah, let me check the chat, because
Yeah.
Okay, people were commenting. Nice.
Yep.
Cool. You're providing some links there too, so that's cool.
Yeah, I tried to kind of supplement as we went along for things for people to look at. One thing I would say is a big problem when it comes to things like grid search. If you have like a lot of data, right, it can start to get unwieldy in terms of like a bunch of data or a bunch of parameters for that matter. Data. And so, have you run into any ways to, you know, optimize that, right? Like, what ways do you know of that you can optimize the time?
Right. So this actually, this entire thing came from my assignment from my master's, that we had to actually compare 5 learners on 2 different data sets. And as you can see, the pipeline that I showed you guys that I built, and it's on the collab, it's a very solid pipeline, and it makes really easy for you to swap data sets and kind of just run everything. Like, really the only thing that you change is the X and the Y, because everything else is going to do for you, as long as you kind of have a data set that does not have any missing data, or you don't have to do any sort of very heavy pre-process up front. You can easily swap, and you can just run everything, and it's going to run for you. And I create so many like different graphs. But regarding your question about the size of the data, I had one data set that had like 20,000 rows, and that was taking a lot to train, especially on support vector machines, because they like are very finicky how they find their kernels and stuff like that. So what I did was I just cut down the data set to, I think it was only 2,000 rows, which is only 10% of the data. But the thing that I did was I used stratified sampling to do that, to kind of keep that representation or the distribution between the classes of the data set. So even though it's a much smaller data set, it still has all of the relationships preserved from the bigger one. It's just on a smaller scale. It's kind of trying to represent the entire US population with like 1,000 people. You know, like how you do that. You got to make sure that you choose 1,000 people that represents the entire thing. So that's what I did. I just used stratified sampling. I reduced the data set to a very small amount that was very manageable. And I did all of my training on that data. And then once I was getting more results, then I could expand the data and see how I could tweak. But then it made that iteration between doing the randomized search and kind of finding the parameters that best fit the data really easily. And then later it could do a grid search to fine tune those parameters. So basically just, I guess a short answer would be just make the data set smaller.
Right. Another thing I might add to that is you could also make your number of folds smaller, right? So when you're doing your K folds during training, you could use a smaller number of those. I mean, you were using 5 in this presentation, so going much smaller is like, you know, and there's always trade-offs, right? Like even with stratified sampling, you lose signal, right?
Yeah,
because it's a smaller data set. Or with the K folds, you're going to lose out because you have less folds that you're training on, and therefore you're not giving as much information to the model. So yeah, there's a lot to consider with this stuff, but I know that you've already given people a lot of stuff, and we could talk about this for hours because this is just data, choosing the data, and how you're, you know, sampling that is a talk in and of itself. But
yeah, another thing to notice that I didn't even mention was that even the models without tuning at all, they already performed so good. Yeah. Like a decision tree with only one depth, which is like just splitting the data once, it did like better than 90%. And that's just like without doing any kind of oversampling or anything. And that just means that the data that I was dealing with, it's really good data. And you know, it's a data from Scikit-Learn, so it's one of those toy data sets, and the purpose of them is, you know, for you to play with the models and kind of see how the models change. So yeah, data is king. Really, the data that you use is going to determine how well your model is. There is no amount of hyperparameter tuning that you can do to like make your data better. If you have bad data, you're going to have a bad model. It's really it.
Yeah, and one thing I would add to that is sometimes you do have a data set and you think it's great, and you train a model and that's great, and then you test, right? But if you have the wrong data set that is not representative of what your model will see in production, you could do all the things right and think you have the best model in the world, but as soon as it hits production, you're going to notice pretty quick right, that you have done something seriously wrong, because that production data, you know, whatever data set you used may have not been representative, and you get some wonky stuff happening. So one thing to note is that ML models won't tell you if they're bad models. That's the part about the, you know, understanding how the model works, understanding your data is really going to give you that information. So that's a skill that like you can't automate away, right, at this point.
Yeah, no, absolutely. That's a really good point.
And Ian said you could just get false confidence from data leakage. Also an whole other topic, right? Data leakage. So, but I know in the interest of time, I'm going to cut the conversation, but Murilo, man, thank you so much for coming. That was awesome. I'm going to play with those notebooks because it's been a while since I've touched Scikit-Learn. So that's really cool. Yeah. And I'll have the video posted on YouTube. So just so everybody's aware, if you want to refer back to the video, I'll be sure to let everybody know when that gets posted.
Cool, man. Awesome.
Right on. Well, everybody have a good night. Murilo, thanks. Really appreciate it. If you have another topic, feel free to come back. We'd love to have you.
Sure.
And I'll see you later. Probably.
Yeah, see you, man.
All right. Bye, everybody. Have a good night.